All right, trucking right along here. Orthogonal sets. So now we're going to start talking about not just two vectors being orthogonal to each other, but multiple vectors being orthogonal to each other. And we say that a set of vectors is an orthogonal set as long as each pair of vectors is orthogonal to each other. Right. So an example of this, right, are the axes that make up our xy plane are an orthogonal set. Right, so the set 0, 1, and 1, 0, or the things that make up that identity, this is an orthogonal set, which I hope makes sense. Now, if we take that into a third dimension and we add in that z-axis, now we end up with 1, 0, 0, 0, 1, 0, and 0, 0, 1. And again, if you think about it, these are also an orthogonal set, which is nice. Right now, what we want to talk about is, well, what if we're not on any of those axes? Can we still have an orthogonal set? All we need to do is show that each pair is orthogonal to each other, or each pair of distinct. Notice it says distinct, so they have to be different, and they can't be part of the same line. They can't be part of the same vector, so distinct means very, very different. We also don't need to check things with itself because you're not distinct if you're talking to yourself. Man, I've been talking to myself a lot. Okay. So all we need to do is make sure that the pairs are orthogonal, and if the pairs are orthogonal, then the set is orthogonal. So here, because we have three pairs or three sets, we're three vectors, we have three vectors, so we need to test three different sets. Right? So we need to see if U and V are orthogonal. We need to see if U and W are orthogonal. And then we need to see if V and W are orthogonal. And the way we're going to do this is by taking the dot product, or the inner product, whatever you want to call it. I like dot product. We're going to stick with it. Dot product just says take your things, multiply, add them. Oh, jeez. Okay. So the dot product of U and V. So U dotted with V is going to give us 3 times -1 is -3, plus 1 times 2 is 2, 1 times 1 is 1, -3 plus 2 plus 1 is 0. Yay! So these things are orthogonal. So that means U is perpendicular to V in whatever plane of existence they happen to be in. Okay? It's orthogonal, perpendicular, whatever you want to call it. I don't care. Have a grand old time. Just, don't let a real mathematician hear you talking such absolute nonsense. Just kidding. Okay. Ooh. U dotted with W. Now we're just going to take this guy and this guy. So 3 times -1/2 is -3/2. 1 times -2 is -2. 1 times 7/2 is 7/2. This is equivalent to 4/2. -3, -4, -7, -7/2. Oh, hey, look at 0. So that means that U is perpendicular to W. All right, so we're on a good track here. Now, we've only shown that U and W and U and V are perpendicular. We have to show the last one because if you think about this idea of perpendicular, so if this is U, I could actually have a vector this way and a vector this way that are not perpendicular to each other, but are only perpendicular to U, right? That kind of makes sense. So it's no guarantee just by checking 2 of them. I have to check this last set in order to make sure that we don't have a situation like this going on. What we want is all of them to be perpendicular to each other in one way or another. Now that doesn't actually mean that they have to sit in the same plane. They just have to be perpendicular to each other. Okay. So no, we're done with you. You can go away. Sorry. Are you guys tired of my dad jokes yet? All right. V dotted with W. -1 times -1/2 is a +1/2. 2 times -2, -2. Whoa, -4. We can do math. 1 times 7/2 is 7/2. 7/2 plus 1/2 is 8/2, which is 8/2 is 4. This is 0. Yay! So that means that the set. Oh God. Too many buttons. All right, so that means that the set containing U, V, and W is an orthogonal set, which is great. And the fun part about this, so if it's an orthogonal set, so hopefully your brain just went, oh wait, that means they're pointing in different directions. They're not all sitting in the same plane. Because they're not all sitting in the same plane, they must be linearly independent. And if they're linearly independent, then it must be a basis for the subspace that's spanned by S. Look at that. It's beautiful. That's just lovely. And if it is a basis, so if it's an orthogonal set and it's a basis, we call it an orthogonal basis. Yay. Okay. This one's fun. And we're going to do some interesting things with this. So this theorem says that I'm going to have an orthogonal basis, which means that I need to have an orthogonal set, which means that all my things have to be orthogonal to each other, and that it needs to be a subspace, that it needs to represent all of W. For each vector in my subspace, remember, we define a subspace by being linear combinations of a vector, and those linear combinations have to maintain space in that subspace. Okay. So the basis here, all this is doing, this U1, oh, I thought that was a highlighter. It wasn't a highlighter. It was just crossing it out. Here we go. This one. Those, if they're a basis, it's the bare minimum you need to create that subspace W. And if it's a subspace, it follows those, 11 axioms that says, 11 axioms plus the 3 that say it's a subspace, whatever. Basically, it boils down to everything in W needs to be a linear combination of the vectors that make up the basis. Okay, that's sort of the definition of what's going on here. So any y, as long as these things are all perpendicular to each other, we can find the weights, or in other words, we can find the constants times the vectors that is going to give us any y by using this formula here. And those constants we'll find by taking the dot product of y and the vector in each position divided by the dot product of the vector itself, of the u vector itself. So this makes a little bit more sense in action. But the nice thing about this is, oh, hey, apparently the whole background's green now, just in case you were wondering. Just losing it. It's kind of fun. All right, we'll roll with it. So first off, so we've already decided that this is an orthogonal basis, which is great. Hey, and if you were, being savvy, you would look ahead and you would have answered the question at the beginning with, hey, yeah, it is, because you told me so down below. Work smarter, not harder. All right, we want to know, if this is my vector y, what combination of these three vectors would I have to add together to get y as the result? And I could, so the way we've handled this before is by taking our augmented matrix and saying, right, so thinking about the creating an equation, right? So C1 times U plus C2V plus C3W should equal y, right? Which means we could treat these as individual, as our constant, as our, so right, C1, C2, C3, and then this would be the matrix made up of U, V, and W, right? And that would give us our y vector. We're doing it in vector. And so what we would do is we'd take those vectors, we'd put them in a matrix, we'd augment it with our y matrix, we'd do a bunch of our row operations, and that would give us C1, C2, and C3, which is great if my vectors are not orthogonal to each other. If they're orthogonal to each other, we can do this by doing, instead of those row operations and trying to keep track of those, which at this point I've said, should be old hat, and you could probably do them in your sleep. So really, it's a, 6 in one hand, half dozen in the other. Decide how you like to do this. Now, again, this is only possible if it's an orthogonal basis. They have to all be perpendicular to each other, have to all be orthogonal to each other in order to use this process for finding our constants. But here we go. So C1, so our C1 constant, we can find that by taking the dot product of y with our first vector. So we're finding this. So the u in this case is always going to be this u because we're finding C1. So the dot product of y and u is 6 times 3 is 18, sure, plus 1 minus 8. So that should give us, what, 11? Divided by, this time I'm going to dot u with itself, which really just means I'm going to square each of these things. So I'm going to get 9 plus 1 plus 1, and I get 11 over 11, which is 1. Okay. Now, up to you whether or not you think this process is faster or slower than doing this augmented matrix process. Might be, might not be. Depends on how much you like your arithmetic skills. All right, so C2, now I'm going to be concentrating on my v vector. So I don't care about u anymore. I only care about the v vector. So I'm going to take my y, and I'm going to dot it with my v vector. So it's going to give me a negative 6 plus 2 minus 8. And then I'm going to square each of the terms in v. That's my v dotted with itself. So we have 1, 4, 1. So negative 6 is negative 14, negative 12 over 6. So negative 2. And last but not least, we'll find C3. C3, again, we're going to deal with our w vector. So we're going to dot the y with the w. 6 times negative 1/2 is negative 3. Minus 2. Minus half of 8, negative 4, negative 28. I'm hoping on a prayer here. And then w dotted with itself, this is negative, or it's positive. It doesn't matter, it's always going to be positive, right? Our denominator is always going to put positive because we're talking about dotting with yourself, is 1/4 plus 4 plus 49 fourths. Is excellent. This would be 16 over 4, 49, 50, 66 fourths. Am I 49, 59, 66 fourths? Yes. So this is 66 fourths. Right? Yeah. 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 We'll go with it. 28, 29, 30, negative 33. Oh, hey, that actually works out pretty good. This is 4 to 2, negative 2. Negative 2, I think, right? Does it have negative 33 times 4 over 66? That's going to give me a 2 down there and a 1 up there. Hey, yeah, look at that, negative 2. Okay, so that means that, you ready? So if I do u minus 2v minus 2w, I should get y. And if you're feeling fancy, you could try it out, see how it goes, and double check my arithmetic. And if I fudged it up, you let me know. I can't wait. Okay. Sorry, the dog keeps barking. She's just on a chair. Okay. So here's where we get a little funky. We get a little out there. But this is also an idea that comes up in Calc 3, is this idea of vector projections, or an orthogonal projection. So the last theorem that lets us break y down and express it as a multiple of all the vectors that make up our vector space, or our orthogonal set, it allows us to think about expressing any vector as a multiple of some other vector and a vector perpendicular to it, right? So in other words, if I take and so here's my vector y, and let's say I have some vector cu, or so here's some vector u, and it was all started 0, 0, and some vector perpendicular to u. So I'm going to so z is some perpendicular, so what I'm going to do, this here would be c times u, and what I end up with is, if you think about addition, right? So we'll let this be z. So hopefully you can see, if I take cu plus z, the vector addition says go and make that is the diagonal of the parallelogram that's going to be created there. So y is equal to that. Now, we just said that we can, what did we say? We said a thing. We said a thing. Now, what we're going to do is we actually redefine, and we redefine this c times u as, we call this y hat. And this y hat is called the orthogonal projection of y onto u. So if you see here, it's kind of like, what would be the shadow created if the sun was directly, it won't make it yellow. If the sun was right here and it was shining down on top of you, and u needed to be reflected down onto, or y needed to be reflected down onto this u surface, whatever that u surface is, I want to know what's its shadow. So this cu, this y hat, is like the shadow of y onto the u vector. Now, sometimes it doesn't quite fit. Sometimes u is a little bit shorter than that shadow would be, which is why it's c times u. Sometimes u is a little bit longer than what that shadow would be. And, aw, how cute. My dog and my cat are just like inches away from each other, cuddling on the floor. It's adorable. So, so the projection of u onto v, or of y onto u, Jesus, is the orthogonal projection. And the z component, or that vector that is perpendicular to u that meets up with y, is called the is the component of y that's orthogonal to u, right? So you've probably seen something like this. Again, this is sort of reminiscent of the ideas that you might have in physics with vectors and force vectors. But we don't always call it the same things. Now, L is called the span of u. So again, if I take my u vector here, so let's just take some in some arbitrary space here. Here's u, right? Here's my y vector. Here's y. That's a y, not a u. That's a y. And you can see that if I try to project down perpendicular here, that I don't actually hit my u vector. But if I extend this here, if I think about this being the span of u, then it doesn't matter. The projection has to do with, the projection is somewhere within the span. So this now gives us, here's my vector, this is c times u, and we know that cu is in the span of u, which means that it's part of that line L. And what we call this is, we say that the orthogonal projection of y onto u, or the projection of y, so the way we read this sentence here, this says the projection of y onto L, where L is the span of u, so L is the span of u, is equal to, oh hey, that looks kind of familiar, right? This looked a lot like the c component. This looks like that finding the c in our linear combinations when our vectors are perpendicular to each other. And oh hey, we're gonna make perpendicular things happen. Now this results of this, so the results is a vector. And it's a scaled vector. And so this is the vector u, right? This here is a dot product, so this is a scalar, because it's a dot product. This here is a dot product, so this is a scalar. Do I have enough arrows and circles and colors here going on here? Either way, you have a scalar over scalar times a vector, so the result here is a vector, right? Which would make sense, because it's the orthogonal projection, it's a vector y. To find the z component, if I want to know the z component, right, if I know that y equals y hat plus z, well then z should equal y hat minus y, or y minus y hat. Ooh, order is a little bit important in this case. Y minus y hat. There we go. Right? Hey! Everybody party! Okay. So let's do something with this. So we're going to let y be 7/6 and u be 4/2. And we want to find the projection of y onto u. And then we're going to write y as the sum of two orthogonal vectors. So in other words, we need to find y hat and z. Right? So y hat is defined by y dotted with u divided by u dotted with itself times our u vector. Oh, let's get rid of that. That's not a dot product anymore, so no dot. When you're doing a dot product, you can't just like put the things next to each other and assume it's a dot product. You have to put the dot product symbol or the inner product symbol. Otherwise, it means something completely different. It means you're multiplying the vectors, which you can't really do unless you, yeah, you get it. Okay, so here we go. U dotted with y. So y hat here. 7 times 4 is 28, plus 6 times 2 is 12, divided by u dotted with itself, so 4 squared is 16, plus 4, so I get 28, 38, 40, 20th, which is 2. And this, I'm going to multiply by, and times, I lost my u, right, times u. So I'm going to multiply that by the vector 4, 2, gives me the vector 8, 4. So this is my projection onto u. There's my y hat, which says that if I want z, I'm going to take y hat, so y minus y hat, so 7, 6 minus 8, 4, is going to give me -1, 2. And if we graph these, just for funsies, just to see what's happening here, ooh, wait, hold please. I think I have, maybe, these two. Ooh, let's see. Albums. Ooh, probably not. Okay, well, we'll fake it. Fake it till we win. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 7, 8. We're all in the positive quadrant, so it doesn't really matter. All right, so our y vector is 7, 6. So 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6. So something like here-ish. Okay, so there's y. Okay, our u vector is 4, 2. 1, 2, 3, 4, 1, 2. So there's u. There's u, right? And what we want to do is we want to think about u as being a line, right? So our projection is going to be onto the line that is made by the span of u. And if we think about, so there we go, like that. So this point right here, if we look at it, this should be 4, 5, 6, 7, 8. Oh, hey, look, there's 8. And 1, 2, 3. Ooh, my scale's a little off, but 1, 2, 3, 4. There's 4. Oh, hey, look, this is the vector 8, 4. Right? Looks pretty good. Right, there's our projection. There's our y hat. And our z, if we graph -1, 2, so -1, 2, that's this guy here, which, ooh, hey, looks like he's just the perpendicular version of this piece here. Hey! All works out in the end. It's beautiful. Wonderful. Lovely. I think that's it. Yeah, that's it.